There. Let's make sure the audio is working. Okay. I'm going to go over sets still quickly, but I did blitz through them at the end of the last lecture that we had. So a set is just the same idea as a set that you may already be familiar with in math class. You have a collection of things. Sets really don't have an intrinsic ordering. It's just like a bag of information, right? There's no first thing in the set. You could have a sorted set. And sets, because they don't really have an ordering, there's no like indexing either. There's no thing at index 0 in a set, because that's not really part of what a definition of a set is. A set is just this collection of information. And an interesting property about sets are the information in the set has to be unique. You can have something called a multi-set, that you can have duplicates of stuff. But that's not what we're talking about. Here we just have a set, and a set only has one copy of each thing in it. If you try to add multiple things with the same value, it just ignores you. So in this example, I'm making a set, Greg, Anna, Sally, Frank, and Frank. But if I were to print out the set, I would see Frank, Sally, Greg, Anna. Because sure, there were 2 Franks, but it just ignored the second one. You can't add a duplicate thing. If you do, it just ignores you. It won't error or anything, it'll just ignore you. So yeah, notice Frank was in there twice, but it wasn't. So I can add things to a set. There's a method attached to sets where I can say add Lynn, and then it just adds Lynn. Great. There's also, you can also check if something is in with this in operator. There's other ways to check as well. But raise your hand if you've used in anywhere else in this course. Put your hands up. For thing in something, right? But when you use in a for loop, it means something else. That's the syntax for the for loop. You can use in for like Ryan in that set. It'll tell you if that thing exists in there or not. A lot of other data structures has a method built into it called contains, which I'm curious if a set has, so let's have a look. 0, 1, 2. Print. Just make sure everything seems fine. Okay, 0, 1, 2, great. I guess it doesn't. What are the methods there? Clear, add, copy, difference, update, discard, intersection, update, disjoint, is subset, is superset, pop, remove, symmetric. There's a bunch of stuff there. Look at all that fun. But I guess contain is not in there. A set is an example of what we call a collection. It's a data structure, it's a collection, it's something that can hold on to a collection of information. And among collections, there are a lot of common methods that you might have. Contains is one, but I guess in Python, sets don't have that. So this is a way to check contains. Now, I'm going to warn you. If I ever tell you in an assignment or on a test or something, oh, do a linear search for something or other, and you do something to tell me if something exists in the collection or not, and you use the in operator, I'm going to be mad at you. No, not allowed to do that. Because the in operator just does the linear search for you. It doesn't just magically know. Although technically with sets, it's not doing a linear search. I'll come back to that in a moment. But yeah, let's say you have a list and you use in. Is something in here? It'll return true or false. And you're like, well, why would I ever write a linear search? I'd just use in. Well, we're learning how to do the linear search. When you just write in, you're kind of skipping the step. And I said this in lab yesterday, and I say it a bunch of times. It's like taking a class on how to build cars, and then showing up and being like, why would I ever build a car? I could just go buy a car, and it's already made. Why would I ever need to go build it myself? And the answer is, because we're here to learn how to build the car. If you don't want to, fine, but don't come to this class about building cars. So we're learning how the linear search works. So no corner cutting on anything like that. Anyways, sets, the backbone of how a set is implemented is not a list. The underlying main idea of how a set works is actually a dictionary, which we finished talking about. Remember, a dictionary is that fancy data structure that you can index, not with integers, not with numbers, but with like whatever you want, like a string, which is great. And if you want to know if something's in that dictionary, you don't actually have to do a linear search. You just put in the key, and if there's a value there, you know it's in there. If there is no value, well, then you know it's not there. So that's the underlying way that the set works. You add stuff there. Is something in there? Well, you just check if the key exists in the set, and if it does, you're great. If not, it's not there. All right. So it looks like here, I have Computer Science 161 and Math 106. Is anyone in both those classes this semester? A couple people. Okay, great. So you would be in both sets, let's say. And if I wanted to know the answer to the question, oh yeah, you can iterate over a set with a for loop too, whatever. But if I wanted to know who are all the students that are in 161 or 106, right? I want to know all the students that are taking these classes. They don't have to be in both. I just want to know all of them. If they're in one or the other, maybe both, I don't care. Well, that's called the union, a set union. You may have seen this in math class, where you have like union V. This is a union thing. It means just combine the sets, put them together. And if there's a duplicate, if, for example, you two, because you said you were in math as well as this class, if I did the union, well, the resulting set doesn't care that there's two, it just would only have one copy of you. It doesn't add the duplicates, it's just because it doesn't care. So that's kind of like where the value of the set is, like the fact that it is unique and requires, it has to have that uniqueness, that's it's the property of the set, is it kind of gives you the value of like, well, if I do the union, I'm still only ever going to have one copy, which is great, because I only want one copy. You'll notice a similarity between the union and the operator or, because it's like one or the other. But it's not exclusive or, so it could be both. But like if I said, imagine each of these circles here. One circle is all the students in 161, and the other circle is all the students in Math 106. And I were to ask a question like, is this student in Math 101 or 106? Right? That's kind of what this is doing here, right? Well, if you're in either of those circles, maybe both, yeah, it's valid. That's you're included. Right? So it's kind of like or. Then there's the intersection. The intersection is kind of like, well, only tell me if they're in both. And this one's more similar to and. Are they in 161 and 106? If I did the intersection of those two sets, the resulting set would be the students that are in both. But they have to be in both. And then there's the set difference. And this is the weirdest one. It's really not that bad, but when you're first learning it, it's the one that throws people off a little bit. Because with set difference, the order matters. If I said 161 union 106, or 106 union 161, the order of the operands don't matter. Same with intersection, right? It doesn't matter what comes first. But with set difference, it does, because it allows us to ask us which elements are in one set, but not the other. So it would tell me which ones are in 161, but not in 106. And then it would be a different answer to the question, who's in 106, but not in 161. After I've explained all this, I will say, there will be no question on the exam about sets or anything, right? I'm just kind of talking about this as a data structure. We've seen lists, we've seen tuples, we've seen dictionaries, now we've seen sets. Lists are the big ones. But sets are really handy, and they're really handy for the times you need to use them. When you're like, you know what, a set would be perfect for this, it's gonna be perfect for it. It's kind of hard to explain. When you need to use a set, it's going to do exactly what you need it to do. But you're not going to need to use a set that often, probably. We will in 162, but anyway. And so here are some thought questions. If I wanted to count the number of unique words in some text file, maybe it's a text file containing all of the words from... Maybe it's a text file of Alice in Wonderland. And if I load that in to Python and throw them all into a set, because the set ignores duplicates, it only ever has one copy of things. If I loaded all the words into a set and just took the size of that set, the cardinality, the length, it'll be, well, the number of unique words. Because the word the probably exists a lot in that book, right? But it'll only ever occur in the set once. Then if I wanted to say, well, what words do they have in common? If I loaded up another book, it's the time machine or something, and I want to know what words exist in both books, right? Well, I can just do the intersection of those two sets. Maybe there's words in Alice in Wonderland that don't exist in the time machine. If I want to know which were in all, like how many words were in both books that were unique, union. If I wanted to know which words were in one but not the other, set difference. Its usefulness is fantastic for when you need to use it. It's hard to explain. But you're not going to need to use it a lot, but when you need to use it, oh, it's amazing. Any questions about that? It's a weird thing to talk about because it's more, the point of this part right here, oh, was that your computer? The point of this is not to be like, learn this, these are sets. The point of this is they exist. You might come across a time when you're writing a program where you think, sets might be helpful. Then this is to make you aware that they exist. So if and when the time comes, you know they exist, so you just go look how to use them when you need to use them. Cool. All right. Next topic, debugging. Raise your hand if you had to debug your code at some point so far. Put your hand up. Obviously you have. If not, that doesn't mean you're really good at the class. That means you've never written a line of code. So the point of this lecture is not to teach you these debugging strategies. I'm going to talk about some debugging strategies. It's not to teach them to you. But it's more likely that what I'm about to talk about are strategies you have already done. But by showing you some of the common strategies or things people do for debugging, it's kind of nice to be reassured that, like, yeah, that thing you've been doing to debug your code, that's what everyone does. That's good. What you came up with is a great solution because it's what everyone else is doing. Because at this point in the class, obviously you've been debugging. And obviously you have come up with some sort of strategy for debugging your code. So, yeah, we've written a few algorithms, we get bugs, whatever, bugs. Okay, the importance of debugging. Well, obviously, if you write a program to solve a problem, you want to know it's correct, right? No sense in giving me a solution that's full of bugs because it's not a solution. As our programs grow in complexity, it becomes harder and harder to debug. And that should be a fairly obvious statement. The more complex the function is, the harder it is to debug. So the first thing you're going to want to do for debugging is hedge against having to debug complex things in the first place. Break your problems down into nice little functions. Nice little simple functions where you can. Test those. Know they work. If they don't, debugging the simple problem is a hell of a lot easier than debugging the complex one. But if I know all those little pieces have been debugged and work along the way, when I need to finally write that complex piece of code, and I know they all work, I'm in a much better situation Then if I just started to try to write all that code and hit run and it doesn't work and I go, uh-oh, what am I going to do? So the first strategy is hedge against having to debug complex things in the first place. Be very defensive in how you program. Okay. You've seen error messages. Things like this, invalid syntax. Have you ever seen invalid syntax show up? Of course you have. And those types of things are relatively easy to debug. Not necessarily, but relative to the logic errors, these are easier to debug. Raise your hand if when you did the linear search, it worked sometimes, but it didn't work other times. So that would be like a logic error, where like the code ran, and it was like, yep, I'm doing what you told me, I'm happy with it. But it didn't do what you want. That's a logic error. This is like a syntax error or something. Fortunately, another thing nice too, sometimes you'll get these error messages that make no sense to you. Python's actually pretty good. Python's pretty nice in its error messages compared to other programming languages. Some other programming languages just vomit numbers at you and you're left going like, what does that mean? But when you get a nice error message like this, if you don't know what it means, just throw it into Google because you're gonna find the solution like that. So that's another reason why error messages, when Python throws an error message at you like that, it becomes a little easier to debug because you can have some guidance to begin with. But when you have a logic error, like that linear search one where it worked sometimes but not other times, you can't, good luck Googling that one, right? Be like, my linear search works sometimes. Well, that one's going to be a harder one to find. So common things you're going to see that give you an error message are things like your syntax error. Raise your hand if you had that one. How about an indentation error? Ever have an indentation error? How about a name error? Have you ever seen like unresolved name reference to variable? Put your hand. I know you have. You just haven't realized you have. Type errors. Have you ever? Yeah, you've had that. How about index error? You ever get an index error where it's like an index out of range or something? Yeah, you're going to get all those. These are very common. These are very common. And do not think for a second that these are the folly of new programmers. These errors, experienced programmers get daily. You know, they're waiting until they hear, oh, shoot, oh, yeah, okay. The only advantage they have is it's not that they're not going to make those mistakes. Sure, they might make them less frequently just based on experience. But the advantage the experienced programmer has is they've seen those errors many times, so they know the likely suspect as to what caused it. That's the advantage they have. That's what the disadvantage you have is you just don't have that experience yet. So don't think for a second that programmers don't see these. When you hit run and your code doesn't work, yeah, that's typical. That's what you would expect. It would be insane if you sat down and wrote a giant program and hit run and it worked the first time. That doesn't happen ever. I totally did it once though. I'm telling you. All right, syntax errors, right? So if I wrote this, who can spot the syntax errors here? Let's go around. What do you see back there?
The bracket in the definition.
Oh, I got my parentheses the wrong way. So there's a bug. Any other issues? What do you see?
2 F's in define there.
Oh, I spelled def wrong. I put def. What do you say back in the corner?
Walrus is a variable that's assigned to nothing.
Yeah, it just says walrus. I don't know, maybe that'll throw a bug, maybe it was defined, maybe it's just there and it's not doing anything. Either way, it's not particularly helpful. And then you had your hand up too? Oh, I missed the colon. Yeah, it should be a, close parenthesis, colon, indent, yeah. And there's one more, what do you say?
That plus multiply 3 will work.
Yeah, Python's gonna be like, well, I can't add a to the operator multiply. That's not a thing. Did you see something else? Broken. Well, that's not it. That's just I intentionally called it Borkin. What do you see?
But you don't call the function working, you're calling broken.
Oh, you're right. I would have got a name error. Shoot, you're right. Oh, yeah.
There's 2 F's on that.
That was already said, but yes, you're correct. I think we caught them all. Yeah. So there'd be a lot of issues here, right? Let's see what happens if I actually write this into Python. All right, first thing, invalid syntax. It's pointing at the n. I'm not 100% sure as to what it's referring to because there's clearly no issue with n. But let's assume it's this. So we fixed that, we hit run. Still invalid syntax. Okay, let's try the colon. Still invalid syntax. Okay, you know what? I'm wondering if it's the def. So let's go back and change the def first to see if that... All right, okay, so it was def. So we fixed def. We'll fix the parenthesis. Okay, it's telling us we're missing the colon. Invalid syntax, yeah, you can't add a number to multiplication. That's not a thing. Broken is not defined, right, because it's Borken. And then name error. Walrus is not defined. It's telling you, what the hell? That's just not a thing. Why is it there? And finally it works. There we go. Cool. Raise your hand if you've ever debugged something in a similar strategy. Run, no, oh, fix it, run, oh, fix it. Of course. That's what you do. But these are the simpler, not trivial, but simpler things to debug because those error messages can be quite helpful. Type errors. Type errors are funny in Python compared to other programming languages. So Python's pretty good at figuring out types, but like if I say 99 plus bottles of beer on the wall, it's going to say, no, you can't, that's a type error. I can't add a string and an integer together. I can't do that. It's not an option. So that's a type error. Some programming languages are a lot stricter with types, and this bug would come up to begin with. But where the type errors arise comes up in different places in different programming languages. But the point is, a type error is a situation when you're trying to do something that's not defined for a certain type. If I say add these two strings together, you go, oh, well, Python, that means concatenate in Python. If I say add these two numbers together, that just means addition, which you've known since you were this big, right? But if I say, what's hello plus 3? You're all looking at me like that's not an admissible question. That's absurd. And Python is telling me that's absurd by trying to add 99 to bottles of beer on the wall. How could I fix this? Let's try you. Hello.
Make 99 a string.
Make it a string. Yep, that's probably the easiest way. Just wrap it in str, right? That's what you're saying? There you go. Could also done f strings, could also do, there's a bunch of other ways we could fix it, but that's probably the easiest. Convert it to a string, so then it's happy adding a string and a string, which is what we wanted in this situation, but yeah. Although there would be no space between 99 and the B, whatever. Yes?
Add a space between the first bracket and the B clause.
Like right here?
Yeah.
Yeah, that's what I would do. Just start that string with a space. Problem solved. Okay, this is a funny thing about Python. Because Python is not that strongly typed. So here's a function called inconsistent. It takes an A and a B and it returns A plus B. But depending on the type, so this would be an example of an error that won't raise an error message. And maybe it's not necessarily an error, but it might be. And this often happens when doing input. And let me show you with input, because that'll make more sense. I may have shown you this one already, and if I have, just go with it. There. This is effectively what that function is doing. I just didn't do it in the function, okay? If I hit run, What this is asking me to do is enter a number and then another number, and then it's going to sum them and print them out. So if I put in 1 and I put in 1, I should expect 2, right? 1 plus 1 is 2. But I get 11. Raise your hand if you know why I got 11 and not 2. Raise your hand if you're like, why the hell is it not 2? So the issue here is, if I was expecting this to do addition, I made a huge mistake. Because it's not doing addition. It's doing string concatenation. Because Python will assume everything that's inputted is always a string. So this type of bug, you have code that requires addition. 1 and 1, the result better be 2, because that 2 is going to be used in a bunch of other places in the program. It's a very important cog in the whole machine. But I put in a 1 and a 1 and it gives back 11, and then that 11 is being used elsewhere. We've got a big problem, right? So this is an issue caused by kind of mismatching your types with what you really wanted. This really would be more of a logic error in Python. One way to hedge against this in Python would be your type hints, right? I didn't have type hints here. If I said inconsistent A, it's an integer, and B is an integer, and it returns an integer, that tells the programmer, this reminder, these are supposed to be integers. But having the type hints won't stop Python from making the same error. Python's type hints aren't for Python, they're for you, the programmer. Other programming languages that are more strongly typed, like Java, that we're going to do in 162, whenever you have a variable or a parameter, you have to specify its type. So when writing your function, it would be like having a type hint where A is an integer and B is an integer, but where Python just ignores the type hints. The type hints are for you, the program. Other programming languages like Java would be like, you just gave me a string and I expected an integer, so I'm not going to run. So it would return an error, where Python doesn't. A lot of people think Python, it's funny. I think Python's my favorite programming language to start teaching people how to program. But then you get to a certain part of experience and expertise where suddenly Python becomes a terrible programming language to continue to learn how to program. Because Python's flexibility makes Python accessible at first, but there's a point where that accessibility actually gives you a lot of extra rope to trip yourself up with all the time. So this is just one example where sometimes the limitations and constraints of other programming languages actually help you avoid bugs before they even happen. But that'll become more clear the more experienced you get. All right. Logic errors. These are the big ones. These are the ones where you wrote your code, everything's totally right, I hit run and it didn't work. My cert test didn't pass, something's wrong. Something's wrong in the code. The program runs fine, it doesn't crash. I made this function, I give an input, I expect this output, but I got an entirely different output. Something's wrong with my code. This would be a logic error. And again, like I said, the best way to debug these logic errors are to hedge against having them in the first place. Have smaller, simpler functions. If you find yourself writing a big complex function, does it really need to be, can you break it down into simpler bits? The first and probably most effective, given how easy it is to do, is add print function calls throughout the function. Here's what I mean. I've got something like my linear search. Or I just have, do I have an example? Here we go. Sum numbers up to. All right, so sum numbers up to, I give it n, it wants an int. This function adds up all the numbers from 0 to n exclusively, meaning it won't, like if I put 5, it won't actually include the 5. So if I put in 5, it's 0 plus 1 plus 2 plus 3 plus 4, which is a total 10. Okay? That's what it's supposed to do. And I hit run, it fails. I put in 5, it doesn't give me 10. When you look at this code, maybe you've already spotted the error, but that's not the question I'm asking. The question I'm asking is, when looking at this code, is it immediately clear where the issue is? No, it's not. And realize for a moment, when I start talking about complex functions in code, look, that is a small function. But I'd sure as hell say, I mean, that's not trivial. There's complexity in there. There's a loop. As soon as you see that, good luck keeping track of the values in your head right away. So here's what you do. First time through the loop, what's the value supposed to be? Second time through the loop, what's the value supposed to be? Third time through the loop, and so on and so on and so on. What's it supposed to be versus what is it? The easiest thing to do is, okay, print C. Okay. Throw in a print there. I hit run. Okay. First time through the loop, I see a 0. Second time through the loop, I got a 1, then a 2, then a 3, then a 4. So that makes sense, right? Now let me ask you something. I'm going to give you 15 seconds. Look at the code. Look at the output from where I put my print. And I'm going to give you, maybe I'll give you 30 seconds to see if you can find where the bug is. Just on this output. If you found it, great. Just raise your hand if you found it. Okay, I'm going to give you a minute. See if you can figure it out. Really. Take your time. How about this? Put your hand up when you found it and leave it up, just because I want to see how the hands go. Your hand might get tired, but deal with it. Now, for those of you with your hand up, when I added that print and you got a chance to see what the value of C was at that line of code every time through the loop, you can put your hands down. By adding this one print, was it the print that made it like, I see what the problem is now? No? Oh, shoot. Well, you ruined my story then. Because to me, it does. To me, I go, okay, at the beginning of the loop, the value is C. I see a 0 outputted. But then right below it, I add 1 to C before I add it to total. Let's move where this print is. Because maybe you haven't figured out the issue yet. So I'm just going to move the print there, maybe see what, oh, okay. So C already has the value 1 before it got added to the running total. And look at the end. The last value there is 5. C had the value 5 before it got added to running total, because I know it was before, because I printed out C at line 14. And then immediately on the next line, it took the value of C and added it to running total. Meaning it added the value 5 to running total. It should not have added the value 5 to running total. Without having the print there, I'm just looking at this chunk of code going, where's the issue? I throw in the print, suddenly I can very clearly see what the value of C is. I know what the value of C should be every time through the loop. But knowing what it should be doesn't help you at all when you don't know what it is and you don't know where the difference is. As soon as you see what it is, well, knowing what it should be and seeing what it actually is, suddenly you can start to solve the problem. I expect to see a bunch of assignments handed in. Every computer science professor that teaches first, second, third, fourth year, the whole time, when we see submitted assignments, we expect to see a lot of commented out print function calls. Because what happens is you're writing big chunks of code, and something's not working, you put a print in there, and then, because this will be what happens, right? Now this is an example of a smaller function, much bigger function could have issues. Maybe you've got this, so you print it, you're like, okay, 0, then 1, and it's still 1, and then 1. So you can kind of keep track of where everything is, but you're like, okay, you know what? I really don't care about what it is right here, so I'm just going to comment that out for now. I'm going to hit run. Okay. All right, so this one's not helpful either. Okay, so I would do that, and then, okay, now I see where the issue is. Okay, I don't need this line anymore. I'm just going to get rid of it. Okay, great. And it works, great. Oh, I didn't fix it yet, though, because there. Now I'm going to fix the function, increment C after I add it to the total. And it works now, great. But you know, I'm writing my assignment, I'm moving quick, because I want to get this done. And I left those prints in there, just commented out, because I didn't want to commit to deleting them yet, because I might need them still. So it is very typical to see assignments littered with these commented out prints. I mean, avoid doing that if you can. Once you're done and your function works, you can get rid of the prints. Sometimes too, it's not about even knowing. Imagine you've got a loop with a bunch of if statements in there. It's not even about knowing what any of the values are. It's when I run this, the code inside that if statement should run. So, like here. These will also happen as well, where you'll just have like flags of like, okay, if I run this and I hit run, okay, so this is working code because sum all the values from 0 up to 0, it's the result is 0. So it works, that's why that assert test is there. But based on this, the loop shouldn't run. So if I run and I don't see any, okay, that's good, it's great. So these are things that get commented out all the time as well. Just be careful what you write in there because frustration could kick in and those strings can get colorful. Just don't offend the TA. You know, stuff like that, right? I won't be offended, but maybe Ethan will. I don't know. Any questions about the print one? Use this one. It's easy. You just throw it in there. What do you want to see? The value of this. It's easy. Use the print. It is your friend for debugging. It's like a joke in programming about like, oh, I know how to use a debugger. So there's something called a debugger, which is a program that helps you debug your code. But it's really sophisticated and fancy. But everyone jokes like, oh, I know how to use a debugger. And then it's like print, right? But it's because it's so friggin' good at helping you debug. But it does have its limitations. So yeah, it's great because you form a hypothesis on what the value should be, you hit run. If it's not what it should be, you know, you're narrowing down the problem. If it is what it should be, well, the problem might not be there, it might be with another value. Pencil, paper. This is another very common one, or preferably a whiteboard if you have it so you don't waste a lot of paper. But one of the most important things to do when debugging is you need to not make any assumptions about your code. And 9 times out of 10, the thing you do that makes it so it takes longer to debug something than it should have is because you assumed something about your code. Never assume anything. It's like what I've saying since the beginning of the semester. What does the code do? What does it say? Follow the code line by line. Never take for granted anything. Never assume anything. And I give you this advice, but I do this all the time. Where I'm trying to fix it, I'll spend 10 minutes on a bug, only to realize that, oh, it's because I assumed that line did this, but it didn't. Or, oh, I assumed that function call that I also wrote was, you know, working correctly, but it wasn't. Never make any assumptions ever. And when I say every line of code, I mean every line of code. I mean, don't be like, well, these 3 lines of code, it's the loop. I'm just going to, you know, I know what it does. No, you don't, because it's got a bug. You don't know what it's doing. Don't make any assumptions. Sheet of paper and a pencil is great because it's a great tool for going through your code line by line. If your code has more than 1 or 2 variables, you're not going to be able to keep track of what the hell's going on, though, in your head. Because chances are you've got a complex function. If you need to debug it, you can't just find a solution like that. You've got a couple of variables, a couple conditions that need to get checked. Maybe there's a loop. I don't know. But when you're going through line by line, you're going to need to keep track of those variables. And you're not going to be able to do it in your head. So write them down. Yeah, whatever. Blah, blah, blah. I just said that. Okay. Write them down. What the heck? There was something I was going to say, and of course now I lost my train of thought. Write them down, line by line. Never make any assumptions. What the heck was I going to say? Yeah, all right, whatever. I can't remember what I was going to say, but great. Pencil, paper. Keep track of the values. Use it. Drawing out abstractly what should be happening is also really valuable as well. In second year, I bought myself my own little whiteboard, and it changed the game completely. Now, this won't make a lot of sense right now because the functions we're writing tend to be like, okay, function, input, output, linear search, great. But eventually, you'll start creating fancy data structures like trees and whatnot. Where a tree is a data structure that looks something like this, where you've got like nodes that has some data in it, I don't know. But the data might, it's got a left and right node. Maybe this one has a couple child nodes as well. This one does, so you've got stuff like this. Being able to draw out. It's not just about keeping track of the values. The values that you have might not be as simple as the string or an integer. The values might be some weird, bigger idea that you need to keep track of that you might need for drawing out and whatnot. Pencil, paper, whiteboard, huge. You're also getting to the point of needing the pencil and paper, not just for debugging, but for starting to solve problems on things like Caddis. You're never going to be able to, every programmer in the world, if you go to their desk, you're going to find it littered with pieces of paper, with chicken scratch all over it. Because it's just where they're writing down ideas, where they're trying to find a way to solve the problem before they write any code. No one sits down and be like, okay, I have a solution, here we go. That only works for a certain level of complexity of the problems. You get a certain part where you need to kind of work things out on paper before you can start running. Another really good one is delta debugging. This is another good one because it's really easy. I would say of these 3 that we've seen so far, the hardest one to do is the pencil and paper one. Not because it's hard, but because your body is going to fight grabbing that pencil and paper for whatever reason. Because you're going to be like, but throwing in a print is so much easier. Or delta debugging is so much easier. Well, it's easier in the sense that, it doesn't require you to physically move and get some paper. But the pencil paper one's a really good one. But delta debugging, great. You didn't listen to me about breaking your program down into little bits. So you didn't hedge against having no bugs to begin with. You wrote a giant chunk of code and it doesn't work, you're stuck. And you've tried the print, you've tried everything, you don't know what's going on. This is where delta debugging comes in. And delta debugging is a much bigger idea than what I'm just about to say, but the basic idea that's very useful for us is you've got a function. It's 40 lines of code long. Comment all of them out but the first. Hit run. Look at the value of the variable if anything got changed. Did it do what you expected? Yes or no? No? You found your problem probably. If it did, all right. Uncomment out the next line of code. Hit run. Did it work? So it's like you're going back in time and writing your function line by line and keeping track of, at this point, the value should be this. And then you can check. So this is a more extreme way of doing the print, because with the print, you just kind of threw it in and you hope for the best. This is kind of like starting from scratch and adding a line at a time. And I mean add the smallest possible unit of computation at a time back in. Obviously, if it's a for loop, you might not be able to just add one line in. You might add like 3 lines in order for that to work correctly. But add as little as possible as you can. Because remember, as soon as you make assumptions about any line of code, you're screwed. Because your assumption could be the bug to begin with. I know it sounds like I'm saying an obvious statement to you, but I guarantee you have and you will, when debugging, make assumptions about your code, spend an hour debugging it, only to find out that your initial assumption was wrong. Even though you all agree, well, yeah, don't assume anything about how it's working because it's not working correctly, so you can't assume. Obviously, it's an obvious statement, but here we are. Last but not least, rubber duck debugging. This isn't a joke, this is a real one. There's a Wikipedia page about it. There you go. The general idea of this is you talk, you explain your code line by line to something. So rubber ducks was the thing that people use. When I learned it, it was called like teddy bear debugging. You talk to a teddy bear, but apparently everyone calls it rubber duck debugging. Is if you have a rubber duck, and you can find, if you go to a programmer's desk, there's a good chance you'll find a little rubber duck on their desk. Not because it's necessarily what they're doing, but because it's kind of like a little bit of a mascot for debugging. So rubber duck debugging. Explain your code line by line. I can tell you the number of times I've been like, my code's not working, I've been trying to debug it for half an hour. And someone else, I'm like, look, buddy, can you just come sit? I need to explain. And I start explaining my code to them, and they haven't said a word. But as I'm explaining my code, and then in this here it goes, that happens so often. Sometimes you might be lucky, you might have a friend nearby. Sometimes your mom might be nearby. Sometimes all you have is a rubber duck or a teddy bear. But rubber duck debugging is another great tool. And I know it sounds like I'm joking. Everything I've said so far, you're probably like, oh yeah, great. These are real strategies that work. Try them out. Seriously. Anyways, have a good weekend. Unless you have lab today, then I'll see you later.